没有蓝色，这是肯定是。
I have an old computer if you want to borrow it. Did it stop? That's right, exit. And exit again. And in worst case scenario, shut them down again and take another memory stick. Maybe it was something wrong with that one. Just shut this one down. That were the old one, but Windows updates that can take the rest of the day. Can't get access to videos. Good news. Yeah, because here, this will now be the... That's a hard drive. But now you can normally you could move them up or down. If this is sort of the sequence, then it doesn't do anything. F12 is only available supervisor into 7. So F12 and then it should be possible to worst case scenario, and you have to Google the exact type of machine that you have, and then ask boot BIOS boot USB. How to access the USB to set it to boot from something else than your own hard drive. I think he should be already set up correctly, so he should be on the USB now. No, you don't have to worry at all, just start the machine. And then do nothing. I mean, you set up these deals, that's just one. You can try to go down there to the USB and then select it, but he doesn't seem to choose it. So, but of course, what you have, that's your CD amount. That should be your but maybe now if you exit, let keep him there, press exit. So you can't make him read from English, strangely enough. I know some machines have problems with this. And some of them they have some lock that is not possible to do from the USB. Especially the CTF machines, they have some security and it's crazy. So, but have a Google into your machine and then see, or else you just have to pay attention. And so. You have it, you are on run. Yeah, this one should be okay.
You need to install Ubuntu?
No, the install Ubuntu that you see on the screen is something I couldn't get rid of. So don't click on it, unless you want to destroy your own hard drive. Then you can click on it. So this is the window, how it should look if everything goes okay. You should have a Linux system already logged in. Then it should be fine. Did you get it? Yeah, good.
På BBC. Yeah.
The coffee is ready.
Gilla. Okay. Anybody else?
Can you make it run? No. The boot sequence, boot option. First should be the USB. You don't have it. Yo, the Kingston Data Traveler. Yeah, that one should be first. And then afterwards you have your own hard drive. That's okay. Kingston Data Traveler is this one.
Yeah, but if
It still fails. Try 7 exit 7 opens. Yes. No. He starts Windows. I know on some machines we have really trouble telling him boot from USB, not from your own hard drive first. And on some machines we can't really do it. Worst case scenario, you have to Google it, the exact model, and ask USB boot.
yeah, I have checked it, but it's a bit different from others.
Yeah.
It's a basic.
Yeah.
It's a basic.
Is there any special command on this key? Because I use old one on my computer. Is there any?
It's an old version, so if you have a newer one, just keep it. That's okay.
Okay.
Jag tror att passen hade någonting på det då. Det blir då
Okay, we I know not all of you are here so far, but we will just continue either way. Now, first of all, some of you never touched Linux before. It's the first time Linux user, no? Okay. I have on the second page just a list of Linux commands. You don't need that many here, but at least you should be aware of them. You can do a lot with Linux nowadays using the mouse, but if you click on this black rectangle up here, you will get what is called a terminal. So think of it as a command window. Here you tell the computer what to do, and hopefully he will do it. Now in Windows, if you do something stupid, like format your own hard drive, destroy all my files, Windows will ask, are you sure? And then you say yes, and then Windows will ask, are you really sure? And you say yes, and then Windows will say, no, I don't believe it, I won't do it anyway. Linux, that's differently. He doesn't ask anything. You tell him to reformat the hard drive, it's done. Destroy all the files, it's done. He doesn't ask, are you really, really sure this is a good idea? So be careful, you have to know what you're doing here. But you don't get any warnings that this might be dangerous or anything like that. Also, that was the reason I prefer to do it like this with a USB stick. Then you don't have to touch your own hard drive. But it's possible from this Linux system now, running on the USB, to address your own hard drive. And you can still destroy all the files there, no problem. So be careful here. I'll tell you when you have a warning. Like this, install Ubuntu, don't touch it. He will then immediately try to install Ubuntu on your hard drive. Goodbye Windows and whatever you have there. Don't touch it. I tried to disable it, but he popped up either way. Some default things. If you click on these OpenFOAM lecture tutorials, you are sort of back to the Windows system. And yes, you could use this Windows system a long way. Now already here you should be careful. On the places listed, you are user Ubuntu and you have your own desktop. So this folder will also part of your desktop. And the file system, that's the file system on the USB. But he found some other file system down here, 300 gigabytes. That's my own hard drive. So now if I right click on this one and say destroy it, format it, my own hard drive is destroyed. So stay away from this one, whatever you have here. These are some of the cases that I wanted to look into in this crash course. So the first one there, it's a daily tutorial. Sort of the first one you should peek into. So you have two files here. One PDF file, describes a little about this case, and a text file. So if you double click on the text file, you just display it. And here you will now have commands, the different commands that you else have to punch in manually. So you can use it from the text file if you like, or you do it manually directly, your choice. The PDF file, that's just sort of an overview over this PITS daily case. It's a backward facing step geometry, sending in constant velocity, backward facing step, and then you have a nozzle at the outlet. It's a turbulent problem, but it's a steady state case, two-dimensional case. So the mesh, something like this, and how to run it, and how to display the results afterwards. So it's sort of a first test case. So you can have a look at this if you like. Okay, I remove this and use it you go the hard way. So how to run OpenFOAM, and also how to check if OpenFOAM has been installed correctly on your Linux system, you write run, and then he should jump to your local user on the hard drive, and there you have a sort of a work directory, or work folder called run. And now if you write ls, he should list all the files present, all the files and folders present at that location, and you see it should be empty. So you don't have anything there. With OpenFOAM, you have a whole bunch of different tutorial cases included with the software. And you should sort of leave the original alone, don't destroy them, meaning make your own local copy here. So you start by copying a tutorial case. So that should now be CP minus R. CP for copy, space minus R, meaning recursively files and folders and subfolders as well. And where should he copy them from? You start by writing a slash. And then these files, they are stored in a folder called opt. Now what is nice with Linux, this terminal window, you have a tabulator. When you start writing a name, and then you hit tabulator, although you have finished writing, he will fill out the rest for you if the name is unique. And also, if it's not unique, pressing tabulator twice, he will give you a list of options at the location where you are standing. So I know OpenFOAM is installed under opt. Now I don't remember the name, so I just hit tabulator twice. Then he will give me a list. Okay, here I have 2 folders under opt. I'm going into this OpenFOAM folder. So now I just write O and hit tabulator again. He will fill out automatically the rest. And under OpenFOAM, you have a lot of folders. Should be one called tutorials. So you write TU and press tabulator. Under tutorials, we are going to look into an incompressible flow. Incompressible, and under incompressible, we now actually have to choose which program to run. Because OpenFOAM is not just one program, it's a whole bunch of programs. We are now going to run the one is called simple foam. So I write simple and press tutorial, and under simple foam you have several choices. Airfoil 2D, it's an interesting one, a nice tutorial if you are interested in flow around an airfoil. Here with the Almaraz turbulence model. We are going to look into the Pitts Daily case. So I just write P Pitts Daily. And now carefully. Now I have written copy minus R and then the entire address to the folder I want to copy. Next you have to inform him to copy it where to. So you write space and then a period, a dot. That means copy from to where you are standing. So now you copy this Pitts Daily folder into your own run folder. So this little period at the end, space period, is quite essential. And you hit enter and it's done. So now I should have a folder in my run map called Pitts Daily. So that is how you copy a tutorial case. And we want to run it. Well, first of all, then we have to access the folder. You go into the Pitts Daily by change directory command, a cd space and then the name of the folder. And here you now have 3 folders. We are going to look into the details later on. One is called 0, one is called constants, another one is called systems. If you want to know a little bit more about them, you can write DU. That's disk usage. Disk usage for the folder you are standing. Then you see this constant folder. You also have a subfolder called polymesh. 0 and system folder, they don't have any subfolders at all. And they are quite small, very, very small indeed. Okay, never mind that. We have 3 folders. The case should be here. The first thing you do is create the mesh. And that you do with a program which is called block mesh. Big M. In Linux, there's a difference between small and large letters. So you just write block mesh, and then hopefully something should happen without any errors or something. So you have some information here, the number of cells, 12,000. We have an inlet, outlet, upper wall, lower wall, front and back, whatever that might be. At least something has happened and no error. And then you run the program. You write simple phone with large F. And then it depends on how strong your computer are. It should use 760 something iterations to find the solution. If you want to have a look at the printout during simulation, you can press Ctrl S. Then you freeze the screen. You freeze the printout. And then you can have a look at it. Different time levels. Time is a little strange. This is a steady state code. Still he uses time. But now he uses time as an iterative dimension, so don't worry about the time. And he's solving the different equations, x, y, for the Newton's second law. The residuals, still a little bit too big. Pressure equations, continuity arrows, epsilon and k. Okay, then you know what kind of turbulence model he is using. And then how long time he has used. To let him go again, you press Ctrl Q. So Ctrl S, freeze, Ctrl Q, release again. So now just let him go all the way to the end. You are running?
Yeah.
You lost.
Yeah, because it's the keyboard.
Ah, sorry, the keyboard, yeah. But then you use the mouse. System. Ah, okay. System. Then you choose layouts and add keyboard. And then you can take the country or language, or if you have a special keyboard. Yeah. So there, play around until you have the correct keyboard, or else you lost, as you say. Yeah. Is it running? No? No, you can't find it doesn't help you. So you have to use the command. Here you start with C1. And then press LS just to see what you have. And you have another one.
就是大概知道，现在看到完 open world 主要是玩
就是把这种根据这个自己做学习，像你刚看到为了今后在系统时代，大部分人也是剧情。
Ah, but that's a different case. So, no, forget it. So, you right now RM.
你只要直接可以用就行，在那基础上做什么东西。
这个是一部分，你调这个东西是一部分，调这个东西是一部分，然后你具体是什么？比如说，因为这个它是因为
有点像就是已经成型的一个软件，不是一个
算不成熟，是这样的，它不是零，它不是零，对，他们在做这种各种各样的，像他那个参数，相当于是运行用参数，然后你要自己编程也行，具体要输哪些参数，就是具体它需要哪些参数，你必须得自己，比如自己求解它需要的几个参数，然后你可以在里面你要跟着其他，比如产生波浪，你还
就是再往里加，
对，然后你
再往里加，再调，相当于像那个自程序的东西。反正他们是有的能用的，就大概念。
它这个是没有通用，因为一般都是要对这个比较费时的，自己写。
这是一个练的。
And then you join CD space
应该是吧？应该是，没有包括
他们说
now you're inside the
这么多年，
now you can
这不多学的。
复原可做很多，
对，还有但方法掌握又是其次。
now there's great
掌握就是这里面的盒子的东西很重要。这个才是真的，因为它本身我们希望这一口气，就是
才调这个月电器，然后现在我怕
我也是想着
结合来用的去。
这个装，大家都是这么。
this is the yeah, this is one.
我是一样，
然后刚才我们也用的是用不到，因为很多软件它是不支持的。
一般路边都开软件，我也开一个。
And then use another O now.
做流体的。
Oh, okay. And then later, and he fills it out if it's unique. Yeah. And now, I think is enough.
所以说，看你做的。
Now incompressible, and then SI for simple, and then PIT,
这算的不对。
and then it's enough.
它这个改了。
And now a space.
但它这个它这个也
Copy from the
Windows
Yeah, so just and if you now run LS, you have a new folder. So now we have copied the entire structure. Yeah. So now just change directory into the folder, block mesh, and then simple folder, and then you should be up and running.
40年有我台式那台有40年。
Det er første som skifter med båten. Jeg ble det gikk på 3 iterasjoner her. I forhold til 760 tror jeg.
Du har en ny versjon.
Jeg så versjonen fått bedre algoritmer eller noe sånt, eller kanskje bare andre.
Altså, hadde du 12 000 serier når du kjører med en blokkmesh?
Totalen på seg der burde
Du hadde 12 000
Ja.
Du har
Kanskje bare få bedre algoritmer. Vi får trene kanskje bare fra eksempler.
它这个算查它的具体功
它一般来说简单的这种也得讲，它是不是有 X？
CD.
这是有它这边是一个。
Yeah, just try the P and then use tab. Yeah. And Now you are inside.
它就根据这个范数，范数来根据不要说是它这个速度，
Yeah, it is. So the big
再
yeah.
加一个就是它设定的速度，如果速度不够的话，我们再用加速的。
And then simple fold.
第一个指它一般是就是上个分是这么的，
Not done? It's done. How about you guys? Are you running or what?
Finish running.
Finish running. Yes. Excellent. So now the simulation is finished. If you want to see what he has done, you can write ls. Then you see you have gotten a whole bunch of folders in addition to the 3 we had originally. And all these numbers now represent a folder. They are sort of light blue. That's the hint that it is a map, a folder. If you write this usage, you will now see he has done absolutely something, yes. The poly mesh folder has been bigger, and all these numbers, they are quite big. So all the results are stored in all these numbered folders. To have a graphical view, we have a program. It's called ParaView. But you start the program by writing parafoam with a big F. Then not only will he parafoam, thank you. Not only will he try to start this ParaView program, he will also try to read the case where you are standing. So you have to be in the correct folder when you start this program. You have to stand in run and then your subfolder, the case, the tutorial you are running. You have to be in the right location. Then you should get a window up looking something like this. So it's a very cheap program. It doesn't cost anything. So it's not that very good. But for the price, it's okay. So he can, quick and dirty, just show you roughly what has been going on here. The important button in this entire menu system is the one that's always green. Whenever he's green, hit it. It should never be green. Because you are going to change some of the setups in these menus, and then all of a sudden he will be green again. So he doesn't do anything until you hit him. So you have to sort of step on him a lot. So just hit him, and then at least he has read something. Now he's green again. Well, you can continue pressing him several times, but normally just once should be enough. So what you have here in this window is now actually the layout, the geometry. And then you choose what to plot. Now he plots solid color and he plots the entire surface. So there you can now start playing around. If you take the surface, and typically here you will have either a pure surface or surface with edges, that meaning he will mark carefully your mesh, or you can use the wireframe. That's a very good one if you have a three-dimensional case, only looking at the mesh. Sadly, the mesh here is quite dense, so you don't really see anything. Now you can start playing around with the mouse. Use the wheel on the mid button, you can zoom in. And press the mid button, and then you can move him side by side. If you want to zoom into the corner here, for instance, on the step, you can do it like that. If you press any of the other buttons, he will then start to flip around, and you will have a lot of fun trying to find back where did I start here? So it's going to go wrong, you're going to lose it. Then this button is the essential button. Get back to the original state, then you have a chance to do it all over again. So play around with it if you like, but normally you will always go back to the initial state. Now let's try to select something else than just a solid color. Here, by default, the pressure and the velocity. And here, this is the absolute value of the velocity vector, not the velocity components. Okay, if I now choose velocity, well, it's a little dark here. I'm still on wireframe here, that may be not so good. I don't need the mesh here. So I change him back to the surface. At least it's a little more clear. And according to this, nothing has really happened. I have something at the inlet here. If you want to know the numbers, what this color means, you can press this legend and get up the numbers, the magnitude. So dark blue is 0, and well, you have something going on here. But this, what you see, is the first time folder of your results. This is the initial conditions. If you look at the time up here, it says 0, and the folder number 0. Now you can hit the play button here, and he will then read all of your files, and you will sort of get an animation of the solution, which is of course not correct, because remember, we have run this case with a steady state solver. The time doesn't enter into the problem at all. It looks like a time development, but it's pure numerical. So actually we are not here actually interested in this development at all, because it's not real. We are only interested in the last one. So we could have jumped to the time level 760 directly. That's the only one we are interested in. And now you have, hopefully, a nice display of the velocity magnitude. The scales here should be correct. So if I now ask, what's the reattachment length? When you do a backward facing step in turbulent flow, the reattachment length should be 6.5, 7. So you take this distance here, and then you start measuring 1, 2, 3, 4, 5, 6. Should be here somewhere. Doesn't look too bad. To get that one more correct, you have the option here to plot the velocity vectors, streamlines. You can look, if you want, have a peek at the pressure. That one is given. But the pressure here, hard to understand. A lot of things is going to happen here, but the pressure differences are not that strong as it will be here with the nozzle. So here you have a high pressure region squeezing the fluid out. So the pressure here, not so easy to understand. If you want to investigate more, this was a turbulent flow, and here you only have the option pressure and velocity. I want to have a look at K and epsilon, but they are not listed. Okay, that is the default, only pressure and velocity. But if you scroll all the way down here, scroll a little down, and then you can see the volume fields. Default, only pressure and velocities are ticked off. But here you can tick off the rest as well. The epsilon, the K, and also the eddy viscosity, if you want to have a look at that one, and click apply. Now you have all of a sudden a lot more options to choose from. Now you can pick the different turbulent quantities to have a look at them. So the K looks something like this. Should we believe him? Not so sure if this is something to believe. Why should you have a build-up of turbulence in this region. Clearly the turbulence is going to be born close to the wall, especially the step here. So he will produce a lot of turbulent activity. And also the activity is transported here, yeah. But why we should have a very huge center of activity here? I'm a little skeptical, I must say. Let's check the epsilon. Up here, sorry. Well, he's almost gone. And also, this is also a question mark indeed. It's very high, the values is very high indeed. Here and then close to the upper wall. But not in this region where we had a lot of K. I mean, these two quantities should actually go a little bit hand in hand. If you have a lot of production, a lot of turbulent activity, well, then the dissipation at that point should also be big. So I don't think they really match. The eddy viscosity, you can choose it, but remember, he is then K square over epsilon. So when epsilon becomes very small, this is going to be extremely big, dangerously big. And also again a question, why should the eddy viscosity be so big down here? That's a little below the turbulent K. So I would say I'm a little skeptical to this simulation here. I don't think K epsilon is a good choice for this problem. Okay, that was para-view for you, or para-foam. Very easy to just very quickly have a look at the results. Just be aware, this apply button, what you ask for is what you get, and don't remember the time development. Even if it is a steady state code, it's the last one that you are interested in. So here I just exit this one. And if I now write just ls, list all the folders, actually I now could have destroyed all these folders. I don't need them, except the last one. That's the only one that I'm interested in. So before I started the para-view, I could have just removed them actually. Because I don't need that development anyway. Not interested. Okay, any questions from you? So you have gotten a little material of an overview, example for this backward facing step, and also here a little information how you can make velocity vectors if you are interested. But I won't bother you with that, it's just cosmetics anyway. Yeah, maybe we should. Yeah, we can have a look at that one. If you do something wrong here, you have messed up the case. Just destroy it and download it again. So if you now, you can write run to jump back to your original run folder. And here now I have my this daily case. I want to destroy it. Destruction, that is RM, remove. And then you have a space -R. And now you have to be careful. -R means remove the folder and file and all subfolders in one swoop. And he doesn't ask you questions. Are you really sure about this? You just do it. All of a sudden everything is gone. So if you execute this command at the wrong place, everything is destroyed. And you have no chance of getting it back. You don't have a waste basket in Linux. So if you destroy a file, it's gone. So this remove everything, that's just a star. Then he will take any name he finds and destroys it. So now, whoops, everything is gone. So be careful where you execute this RM command. If I want to copy the case back, just use arrow up. He remembers all your previous commands. So here I have this long copy the entire case from the tutorial. Shall I just do it again? So now I'm back to the start inside this PITS daily case, where I now have just the minimum setup. I haven't created the mesh, I haven't simulated. So here I now want to have a look into this setup files, just to show you. The editor, you can use the mouse and click on this up here if you like. That's a gedit program, simple text editor. Then he starts with your home folder. So much better here to start it down here. gedit. Then he will start in the correct folder where I have my files. So it's a very easy folder, and now you can start looking into these setup of a case in OpenFOAM. This is sort of the minimum setup you have to have. 0 folder, that's the initial values. Constant, there you find input parameters, physical constants, and also the mesh. And then the system, where you have a lot of chief information of your choice of solvers. As a minimum setup, you have 3 files. A control dictionary. This control dict, that's the boss. He's the chief file. That's the one most important. FV schemes and FV solution, that is the solvers, numerical schemes, and how should you solve the equation system? Should we use simple? Should we use piso? Should we use first order upwind? And so on and so forth. So here I won't go into those. I will have a look into this control dict file. So I open him. And all these input files will be written in the same form. This is a C++ notation. So the blue here, /star, it's comment block, but here foam file, and then these curly brackets, this is the same notation you use in C++. So here, just information into the system, and then finally some parameters we have to set. And the first one, application, that can be interesting if you ever get hold of a tutorial. What program am I supposed to run here? Which of all the different OpenFOAM versions should I run? And here it states clearly simple foam. That's the program you should use here. Start from can be a little bit tricky, and also the start time. Start time, there you say what's the initial state. And here 0. And but he doesn't necessarily start from 0, he starts from the latest time. So if you had a simulation already, but you had stopped it, I mean, you said you stopped at 300 and something, yeah. Then if you execute it again, he will try to start from the highest number he finds on your result folders. He will then try to start from 300. Of course, then he's satisfied, he doesn't go any further, but he will at least try to start there. So sometimes you want to overwrite this. You should start from the start time, 0, no matter what, even if you have some folders lying around already with different results. And again, stop. At the end time here is set to be 1000, and then we are given the delta t, the time step. Why should we give a time step? This is a steady state code. Well, there you give OpenFOAM a hint. Well, actually it's 2 hints. Simple foam is a steady state solver, and a delta t of 1, meaning it is not a time code. It's not a transient code at all. It just uses time here as an iterative dimension. So the time here is not real. The write control, here you can specify how often do you want him to write some sub-interval results. So don't have a too small number here, or else you'll fill up the USB stick with unnecessary data. Yeah, the rest is not so interesting. So I will skip that one. And then have a look into the Pitts Daily case, and now the constant file. Under constant, you find polymesh. Inside here we find the mesh, and then we have two transport properties. First, just the transport. That should now read something like this. You will have the Newtonian fluid, and then just the molecular viscosity, sorry, the kinematic viscosity. All quantities are given like this. A name, then you have a square bracket with, how many are there? 7 integers. This is the dimensions. So it's an SI units, kilos, meters, second, Kelvin, concentration, radiation, I believe, I'm not so sure. I never used them. So here at least you see this is the kinematic viscosity. It's a meter square per second. And 10 to the power minus 5. That should be for air or something, I think. These coefficients here, you don't have to worry too much about. It's something to do with the turbulence model. Normally here, we'll only have one sentence, this one, the viscosity. When you are dealing here with incompressible flows, you never specify the density. It's not into the equations at all. Because the pressure you have been given here, as a result, that's actually not the pressure. It's pressure divided by the density. So if it's air you want to do, then the density is around 1 anyway. If it's water, you have to divide the pressure by 1,000. The other transport properties is the RAS properties, Reynolds averaged. And here you can specify the different turbulence models. And also you have the option here to switch it off. That can be nice if you have a problem that may be laminar in the beginning and then turbulent. You want to test the setup, you run it laminar first. If you want to test the different models, you can go in here into this file, change this one to a really stupid name and try to run it. You will get a crash and you get an error saying, I don't know this model, but I know these. And then he will give you a list of all available turbulence models. So that's a neat trick. Just give him a crazy number there.
I think we can also write dummy, something like dummy.
Yeah, whatever you want. Just as long as you have a name that he doesn't find. Then he will stop and just give you a list of available possibilities here. And that's not only with turbulence models, it's a lot of the other options as well. When you are, say, choosing wall models and other things as well, then you can see what options will be available. Okay, I won't go further now into this, the polymesh. It's called polymesh because open foam is capable of dealing with any number of phases for one volume. Here it's a structured mesh with rectangular cells, and it's a two-dimensional case, so very easy setup. Then you can construct your own mesh. In this dictionary here, it's called block mesh dict. This is the only file you need to construct your own mesh. It's boundary, you don't need him. He's going to be generated anyway when you run this block mesh and creates the mesh. I won't go through it here in this one because it's fairly complex and big. So it's a long file, a lot of logic inside here. So we will look into that one with a simpler case. So I just crash this one, close without saving. and go back to my run folder and make ready for the next tutorial case. So the next test case, that is the square cavity. So again, write run, so you are standing in your own run folder, you have to be here, and you have to create a subfolder here containing your tutorial case. So you start writing cp space -r space and then /opt open foam tutorials incompressible, but now we are not using simple foam. Now we are going to use a program called icofoam. And under icofoam you should have a folder called cavity. And again, space and a dot, a period. Copy from 2. That's the syntax. Then you have your own local copy of the cavity test case. Next, change the directory to this cavity folder. And if you list the files, again you have these 3 initial folders. Write disk usage just to see how big they are. And again, they are very small indeed. It's still, again, a minimum setup you need to run OpenFOAM. These 3 folders has to be present, and you have to have a subfolder called polymesh for the block mesh dict file information for the structure. And then first create the mesh. You write block mesh. And this one should be very cute. It's a 20 by 20 cell, so all over 400 cells. 1 moving wall, and we have fixed wall, and we have front and back. So this is the classical square cavity test case. Top wall is moving. So after now having created the mesh, you write icofoam with big F and execute the code. And he should be finished in seconds. It's a laminar case, Reynolds number is fairly low, and it's only 0.5 in time. Now we are talking a transient code. The time here is not given in integers. You have point something, so this is a real transient code. UX, UI, and pressure, but no turbulent quantities. Okay, laminar case. Let's have a look. Para foam, large F. And click apply. And then you choose, say, the velocity, U, and again you get the initial time. So, okay, the wall has starting to move, but down here nothing has happened. So hit the play button so you can get the time development. And we don't have that many time levels here, nothing much happens. It's a very low Reynolds number, so this is now our solution. If you want to have a look at the mesh, you can choose surface with edges, for instance, just to see that, yes, it's 20 by 20 uniform mesh.